In this section, I would like to discuss about nuclear transmutation, cyclotron, and radioactive dating. Nuclear transmutation means you're inducing a nuclear reaction to happen. Normally, this is kind of reaction would not happen because this is not a spontaneous reaction. For example, nitrogen 14, if you strike it with alpha particle, of course you must have enough energy for helium. Temporarily, helium would go inside the nucleus of nitrogen and you'd have a combined effect like this. You'd have fluorine 18, and then fluorine 18 would break down into oxygen 17 and hydrogen. Now, for a reaction like this, helium needs to have large amount of energy because as helium approaches nitrogen, they are going to repel each other because nitrogen has 7 protons, so that's plus 7 on nitrogen and plus 2 on helium. As they get closer and closer, repulsive force is going to get increased. So alpha particle has to be energized for a reaction like this to happen. And next we'll be discussing about particle accelerators. By using cyclotron, synchrotron, we can accelerate particles. Now, for this course, we'll be discussing mainly the earlier form of particle accelerator, and that's called cyclotron. In cyclotron, there are two D-shaped electrodes that you can see is colored differently. The charges get changed from plus to minus. One of the D's is plus, the other D's is minus. And these act as electrodes. So this is one such electrode and this is the other electrode. And both these are bathed. These D-shaped electrodes are bathed in magnetic field. So what magnetic field does, it bends the path of the particle, charged particle. And that's how particle remains within this, within the volume of D as it gets accelerated. Because as it gets accelerated, the radius of the circle increases. But since it moves in a circular path, it doesn't strike the sides of a D-shaped electrode and doesn't lose energy. So whenever it gets energized up to certain level of energy, then these particles are taken out and they're used in inducing nuclear reaction, which we call nuclear transmutation. Something else I need to mention to you, that particles are accelerated actually when it moves from one D to the other D. Let me show you more clearly here. So this is one D and this is the other D-shaped electrode. So this is plus now and this is minus now. As particle, say this is alpha particle, which is plus, so plus 2 for alpha. As particle comes out, it gets accelerated to the negative D. So by the time it gets out, the charge gets changed. So what is negative now becomes positive. So these are automatically switched. And then it sees alpha particle, let's show you this, this is the alpha, is now accelerated towards the negative. So in this manner, as alpha particle comes out, the charges are switched to the D. So that every time alpha particle is within the gap of the two D's, it sees the negative charge and gets accelerated there. So particles are accelerated in between the D's. And magnetic field, it bends the path of the particle. Now rate of decay or disintegration, that depends upon the number of radioactive nuclei in the sample. To explain that, let's assume that I have only 4 such nuclei. And let's assume that there are 2 decays out of 4, 50% decay. Instead of having 4 nuclei, if I have 8 nuclei, you would expect 4 decays as 50% disintegrates within certain amount of time. That's our assumption. So what you see here is as number of nuclei is increased, number of decays is also increased. So rate of nuclear decay depends upon the number of radioactive nuclei present in a sample. Now with that in mind, we can write down the rate expression as rate equals to Kn, where K is a constant which is called decay constant, N is the number of radioactive nuclei. Now this gives you a first order rate, and we can finally solve it, and you get an expression like this, log of Nt over N0, where Nt is the number of nuclei after time t, N0 is the initial number of nuclei. Then half-life, since this is the first order expression, half-life would be given by 0.693 over K. So nuclear reactions are all first order reactions. And so we can use our known expressions for first order reaction. Let me define half-life with a simple analogy. I think I gave you similar analogy or same analogy when I discussed about half-life of a first order chemical reaction. Say there are 8 birds. After 2 days, you see that the birds has gone down by 50%. After another 2 days, 4 birds become 2 birds. Of course, you know who may be responsible for this, but the number is reduced by 50%, and that's half-life. For this analogy, half-life is 2 days. So how do we define half-life? Is the time interval at which the number or concentration is decreased to half of the original value. And I already gave you the expression for first order reaction, which is 0.693 over K. K is the decay constant. Here we are going to discuss about radioactive dating. And there are 2 ways we can find out these dates. Age of organic materials, which is based on carbon-14 decay into nitrogen-14. Age of rock sample or mineral sample, which is based on decay of uranium to lead. We are going to discuss each of these by going over problems. Now let me first give you a background of how do we determine the age of an organic material which probably died some thousands of years ago. Now, first we need to understand why we consider carbon-14 in radioactive dating of organic substances. In upper atmosphere, of course, you know that our atmosphere has both nitrogen and oxygen, but we have a high percent of nitrogen, about 75% of nitrogen. Whenever there is neutron, the question is, how do you get neutron in upper atmosphere? From secondary cosmic radiation. You know that cosmic radiation comes from outer space, and these energetic radiations strike different atmospheric molecules and knock off neutron, and that neutron can react with nitrogen of atmosphere, and that changes nitrogen to carbon-14 and hydrogen. So this is how carbon-14 is formed in upper atmosphere. Keep in mind, most abundant carbon that we know about is carbon-12. So carbon-14 is a radioactive carbon. Now the question is, how does that carbon get into our cell? This all happens through photosynthesis of plants. Now, when you have carbon 12 as well as carbon 14 in presence of oxygen and lightning, they combine with oxygen, giving two kinds of carbon dioxide. Carbon dioxide with carbon 12 and carbon dioxide with carbon 14. In presence of water and light and the green plants, which has chlorophyll that converts carbon dioxide into sugar or glucose, and this is the sugar we're looking at. You can see that sugar has 6 carbon. Now what kind of carbon you'd have there? Since there are 2 different types of carbon that was part of carbon dioxide, so sugar would have both kinds of carbon already in it. So sugar then becomes part of the plant. Animals get that sugar from plants in the form of food. After the death, there is no intake of food. Since carbon 14 is unstable and it decays, while carbon 12 is stable, this ratio keeps on changing after the death of an organism, carbon 14 by carbon 12. Now why carbon 14 decreases? Because of this reaction given at the bottom. It gives off beta particle, and that changes carbon 14 to nitrogen 14. Let me discuss number 40, page 912. It says that a wooden artifact from a Chinese temple has a carbon 14 activity of 38 counts per minute. So that's important, 38 counts per minute, as compared with an activity of 58.2 counts per minute for a standard or zero age. That means in present day living organism would have 58.2 counts per minute. Counts means how many disintegrations are happening every minute, or how many particles are getting out of this carbon 14, which gives a beta particle. Now, half-life is given 5715, and you are supposed to calculate the time or age. So how long ago that particular wooden artifact was living. So make sure you use this expression, log of nt by n0 equals to minus kt. Now here we need k value, which is decay constant. In order to get the k, we are going to use that known expression. K will be given by 0.693 over t half, which is 0.693 divided by 5715, 5 year, and that gives 1.21 times 10 to the power minus 4 per year. So we got the decay constant, and we're going to use that. And also I need to get the ratio of nt over n0. Let me show you how we can get it. Just take the ratio of those two numbers. 38.0 divided by 58.2, you're going to get knt over kn0. So k and k would cancel out, so you get nt over n0. So now we are going to use this nt over n0 in this expression of log of nt over n0 minus k is now 1.21 times 10 to the negative 4 and times t. So keep in mind this is k value that we already calculated. Now nt over n0 I can now write down as log of 38.0 over 58.2, and that gives minus 1.21 times 10 to the negative 4 t. And after you solve this, so keep in mind this is, now when you solve for t, you're going to get t equals to 3.52 times 10 to the power 3 year. So the age of this wooden artifact is 3.52 times 10 cubed year. Age of mineral sample. Just like in age of organism, we use carbon 14. In this case, we're not going to use carbon 14 because mineral sample or rock sample would not have carbon. Rather, they would have lead and uranium. So the assumption is initially all the rock samples had uranium-238 and it decayed to lead. So this is uranium-238. With series of alpha beta decays, it finally ends up with lead-206. So what we notice here is one uranium ends up with one lead, and that's the relationship we are going to use when we calculate age of a rock sample. So keep in mind, rock sample, when they were formed, they were 100% uranium-238. So in the present day rock sample, if you analyze, you get some lead and some uranium. So the lead that you get is considered to be coming from uranium-238. And on that basis, we are going to calculate age of mineral sample. We talked about this reaction just a few minutes ago, and the problem that we are going to do now would be similar to that of number 15 and 16, which is asking you to calculate number of alpha emission and beta emission. Since we talked about uranium-238 changing to lead, in order to explain to you how we calculate age of a rock sample, let's figure out how many times alpha particles will be coming out of it and how many times beta particle will be coming out of it before it changes to lead-206. So let's calculate this, and if you understand it, you should be able to do both number 15 and 16. So mass change. First, we are going to calculate the mass change in this process is given by 238, that the mass of uranium, minus 206, that the mass of lead. So the difference is 32. Now, since these are nuclei that gives off alpha particles, let's first calculate how many alpha particles would come out. Each alpha particle, just to remind you, that's 2, 4. It has mass 4. Now we can find out number of alpha that would come out of it would be 32 divided by 4. So there'd be 8 alpha particles. You can always double check. 8 alpha times 4, 32, and that's the amount, that's the mass change that had happened. So 8 alpha particles will be coming out of uranium-238 before it changes to lead-206. Now keep something in mind, as 8 alpha comes out, it takes away 2 times 8 protons, because each alpha has 2 protons and it is mass 4. So 8 alpha would take away 16 protons. Okay, now if takes away 16 protons from 92 protons that originally uranium had. So uranium 92 to 38. So as 8 alpha particle comes out, so 92 is now changes to 92 minus 16. That would have 76 protons left after decay of 8 alpha particles. 76 protons will be left, but lead has 82 protons. So lead has 82 protons. So let me write down the bottom numbers, 82 protons, or I should write down here lead 82. How do I get 82? From periodic table. Okay, since it has 82, not 76, so we must have extra protons after 8 alpha particle gets out. Now let's figure out 82 minus 76. So there must be 6 new protons formed. And beta particle, beta emission can convert a neutron to a proton in the nucleus. Let me remind you that this is neutron. When beta particle comes out, minus 1, 0, the neutron changes to a proton. So that means each time beta emission takes place, number of proton is increased. And we want proton to increase by 6. That way, you would have right number of protons to form lead. So that means how many beta particles you need to come and get out? 6 beta. So 6 beta would come out and 8 alpha would come out. So in the same manner, you try to do number 15 and number 16. Let's now go over number 42, page 912. It's a mineral sample and they find that it has, let me write down, 75 milligram uranium-238, so 75.0 milligram of U-238. That's the present day sample, and 18 milligram of lead 206, and that's the rock sample or mineral sample that has uranium and lead. So lead has 206. I think it's hard to read this. So lead 206 and uranium 238 that you have. Now, what is the age of the rock sample? So the question is, what is the age? Remember, I mentioned before that it assumed that when rock sample is formed, initially it was all uranium 238. Because uranium 238 is radioactive, it goes through series of alpha and beta decays that we also discussed in previous slide, and finally becomes lead. So one uranium, it gets converted to one lead. So we are going to use that information. Now, the present day, the uranium that we have in the sample is obviously the leftover after decay of uranium, which turned lead. So this is something, lead is formed because of decay of uranium. Now let's find out NT and N0 value, because you're going to use this expression, log of NT over N0 equals to minus KT, where K is the decay constant, and we can calculate that from the half-life, because half-life is given for this reaction, for this nuclear reaction. So K is given by 0.693 over half-life. That's given by 0.693 over 4.5 10 to the power 9. 4.5 times 10 to the power 9 year. So that gives you, let me write down this separately, 1.54 times 10 to the power minus 10 per year. That's the unit. So we're going to use that in calculation of the age. Age would be the T. Now let's now focus on the value of NT and N0. From milligram of uranium, I can calculate the mole. So first you change it to gram. So multiply by 10 to the power minus 3 or divide by 1000. So 75 by 0 times 10 to the negative 3. Let's write down 10 cubed on the bottom. That's 1000. That gives you gram, and that divided by 238, that gives you mole, and that would be the NT value. That's the NT value. And how much of uranium was decayed to lead? Let's calculate that again. We need to calculate the mole of that. 18.0 milligram divided by 1000. That gives you gram. Divide by 206. And that would give you mole of uranium that decayed. So let's write down here uranium decayed. Pictorially, we are showing you this. At the beginning, you had N0, which is 100% uranium. At the end, the decay portion is shown with dark segment of the circle, and rest is the uranium, which is NT. So N0 would be given by sum of those two values, which is 75.0 divided by, let's draw a line here, 0.0 divided by 10 cubed times 238 plus, because this is the present day uranium sample, which is the first quantity, or NT, plus how much was decayed. That is given by the next value, 18.0 divided by 10 cubed times 206. So this is NT, and this is uranium that decayed. So originally, in order to get the original quantity, you have to add those two numbers. Think about, I have 10 molecules. Out of those 10 molecules, the 5 of them was decayed. That means I had some other molecule. So in other words, the decay has to be added to the present day numbers to get what was the original value. So present day value plus the value, added value, which was lead, but keep in mind it's the same number of uranium that decayed to lead. So this would give me N0, and I already got NT value. So let's now have NT over N0 by N0 would be given by, let's again have this written down, 75, 0. Some of these would cancel out. It's 10 cubed times, I'm writing down everything so that it's more understandable to you. So you'd have 75 divided by 10 cubed times 38 plus 18.0, 10 cubed times 206. Now if you multiply both sides by 10 cubed, all these 10 cubes would cancel out. So 10 cubed cancel out, 10 cubed cancel out, 10 cubed cancel out. Now what I finally get for this is 0.783. 0.783, which is nt over n0. Now I'm going to plug in all these values to the expression. Log of nt over n0 equals to minus kt. Now I can plug in all the numbers. Log of nt over n0 is 0.783. Make sure you double check my calculation. Minus k, which is minus 1.54 times 10 to the negative 10 per year. That's the unit. And t is something that you need to calculate. So once you calculate that by using your calculator, you're going to get 1.59 times 10 to the power 9 year. So that's the answer to this question.